The objective of this lecture is to provide an introduction to kinematics of a point. This lecture will be divided into the following parts. First, we will describe the position, velocity, and acceleration of a point. Next, we will consider how the position, velocity, and acceleration of a point are expressed in various coordinate systems. And these are going to be commonly used coordinate systems. And in particular, we're going to focus on three different coordinate systems. The first one is what's called Cartesian coordinates. The second one is what's called cylindrical coordinates. And the third one is what's called spherical coordinates. We will then provide a brief discussion of the key concepts learned in this lecture. And those concepts include the idea of a rotating reference frame, and in conjunction with the rotating reference frame, the application of the Transport Theorem. So the first thing that needs to be done is we need to define position, velocity, and acceleration of a point. So we start as follows. Let's suppose that A is an arbitrary reference frame. And that O is a point fixed in A. So here's this picture. We have a frame A, and we have a point O, and O is fixed in A. And next, let P be an arbitrary point. So P is some other point. P is out here. Then the position of P relative to O is the vector from O to P. So you say then the vector from O to P is called the position of P relative to O. And we denote that as follows. We say RP/O, and that's the position of P relative to O. Now, using that convention of the position of P relative to O, we now can describe velocity and acceleration relative to reference frame A. So then, given the position of P relative to O, which we've defined as RP/O, the velocity of point P as viewed by an observer fixed in reference frame A is defined as VPA, and that's the rate of change in reference frame A of the position of P relative to O. And this is the velocity of P as viewed by an observer fixed in reference frame A. And using the velocity, we can get the acceleration. So then, given the velocity of P as viewed by an observer fixed in reference frame A, which we've already called VP left superscript A, the acceleration of point P as viewed by an observer fixed in reference frame A is defined as we say APA is equal to d dt in A of the velocity of P as viewed by an observer in A, which also happens to be the second derivative in A of the position of P relative to O. Now, what these definitions establish is if I'm given a position of a point relative to another point, so in this case it's the position of P relative to O, and the point from which I'm measuring distances is fixed in a reference frame A, then the rate of change of the position of P relative to O is the velocity of that point as viewed by an observer fixed in that reference frame. So in this case, the reference frame is A, point O is fixed in A, and I can take the rate of change of the position of P relative to O in frame A and get the velocity of P in frame A because point O is fixed in frame A. So we're going to say that just a little bit more completely right now on the next page. So this is an important point, which is that the premise here, or we're given the following information. We're given a reference frame, which in this case is A, and 2, we're given a point O fixed in reference frame A. It's not fixed in some other reference frame. It's fixed in that particular reference frame. So that implies that the position of P relative to O, this position is measured from a point fixed in frame A. So that, because of that, that implies that VPA is the velocity of P as viewed by an observer in A. And similarly, that the acceleration of P is the acceleration of P as viewed by an observer fixed in A. And the only reason that this is true is because point O is fixed in reference frame A. If point O were fixed in some other reference frame, this statement is not true. It's only true because we're measuring distances from a point fixed in the frame in which we're taking the rate of change. So that's key, is distances are being measured from a point fixed in the same reference frame as the reference frame in which the rate of change is taken. If we were taking the rate of change in some other reference frame, then none of this would apply. But that's the basic construct of position, velocity, and acceleration. We start with one reference frame, and we have a point fixed in that reference frame. And using that information, we can now directly compute the rate of change of the position of P relative to O, where O is a point fixed in that frame, to get the velocity, and then take the rate of change again to get the acceleration. Now, of course, in general, we're not going to be dealing with one reference frame. We're going to be dealing with multiple reference frames. So as a result, we have to work with these multiple frames, just like we had described in the previous lecture when we derived the transport theorem, where we have multiple frames and one frame rotates relative to another. But in order to get started, we just need one frame, and that one frame establishes a baseline, and then we can add on to it as we actually move through what we're going to do next, which is coordinate systems and commonly used coordinate systems in dynamics. So what's going to happen now is we're going to draw a picture, and we're going to keep adding on to this picture as we move through this, to be able to see how these different coordinate systems and play out, and how that adds rotations, and how it it introduces rotating reference frames just by the mere the manner in which the position is being parametrized. So that's the next step. So now let's describe commonly used coordinate systems. Now, the first of these coordinate systems is what's known as Cartesian coordinates. Now, Cartesian coordinates are the most familiar of any of these coordinate systems. And the way Cartesian coordinates work is as follows, is that suppose I have a basis. I have a coordinate system, but let's start with the basis and then we'll put the origin on it. So I have a basis. I'm going to call this basis EX, EY, EZ. And I have a point. And that point again is O. And I'm going to establish the following. First is that EX, EY, EZ is fixed in a frame called A. So I can just put a little A over here just so that we know that this basis is fixed in this frame. And once again, this point O is fixed in A. So it's kind of the same setup I had before, except for now I've put down a coordinate system, and that's important because I need a coordinate system in order to be able to quantify the position. So now imagine that I have a point P. So there's point P. And the vector from O to P is the position of P relative to O. Now, given the way I've described this coordinate system, I can now take the components of this vector in this basis and I can use them, give them names, and I can set up components. Well, what are these components? Well, along EX, I would naturally call that X. Along EY, I would naturally call that Y. And along EZ, I would call that Z. So then, the position of P relative to O is equal to XEX plus YEY plus ZEZ. Now, it's really important. I'm going to say this again. This basis, EX, EY, EZ, is fixed in reference frame A. So as a result of it being fixed in reference frame A, we can now take the rate of change somewhat directly because these basis vectors are fixed in this frame. So using this information, we then have the velocity of point P as viewed by an observer fixed in reference frame A is given as the velocity of P in A is equal to the rate of change in frame A of the position of P relative to O. But because EX, EY, and EZ are fixed in frame A, that's equal to X dot EX plus Y dot EY plus Z dot EZ. Then the acceleration of P as viewed by an observer fixed in reference frame A is given as it's the acceleration of P in A is equal to the rate of change in A of the velocity of P in A, which again, because I'm going to use the last result is the velocity of P in A, I'm going to take its derivative to get the acceleration of P in A, which is going to give me x double dot ex plus y double dot ey plus z double dot ez. Now you'll notice that because we only have one frame at this point, and point O is fixed in that frame, the rates of change, first the velocity and then the second rate of change, the acceleration, is obtained simply by differentiating the components of the vector. The components of the original vector, which is the position of P relative to O, in Cartesian coordinates are x, y, and z, so I take the rates of change of x, y, and z to get the velocity, and then I take the second rate of change to get the acceleration. Now, that works as long as you just have one frame, but in general, we don't always use Cartesian coordinates, and in fact, in many problems, we actually do much more complex calculations, which requires us to use more advanced constructs when it comes to coordinate systems. So the second construct is, now I'm going to define a few things, and I'm going to introduce these things that I define on a diagram on the next page. So this is now what's called cylindrical coordinates. So that's the end of Cartesian coordinates. So now we're going to talk about cylindrical coordinates. Now, in order to be able to do that, we're going to introduce two new variables. We're going to introduce variables r and theta. And we're going to introduce them in not just any old way, but in a way that has a particular structure. And what it's going to be is that x is equal to r cosine theta and y is equal to r times the sine of theta. So now let's go back to this diagram that we had before, and we're going to draw it with some more information on it from what we had previously. So let's look at this diagram again. Originally, I had this basis ex, ey, ez, and this basis was fixed in frame A. And again, I'll draw that in just a second. So I have a basis that's fixed in frame A, and I'll put it down here. So ex, ey, ez is fixed in A. Put a little A here again. And point O is also fixed in A. But now I'm going to introduce these variables r and theta. And the way they're going to be introduced is as follows, is that here's my point P. So it's the same diagram I had before, except for now, on top of what I had, I'm going to introduce these new quantities, which are, remember that I had x, y, and z on this diagram originally. So they remain there. This is x, this is y, and this is z. But I'm going to introduce this new point, which is down at the projection of point P into the ex, ey plane, and I'm going to call that point Q. And the angle between ex and OQ is going to be defined as theta. And the distance from O to Q is going to be defined as R. So let's get this right. So R is the distance from O to Q, and theta is the angle between EX and OQ. And I'm actually going to call the unit vector along OQ, I'm going to give it a name. That unit vector is going to be called ER. So ER is the unit vector along OQ. And EZ remains the same. Nothing changes with EZ. And I'm going to define a new vector from ER, which is going to be the cross product of EZ with ER. So I'm going to say let E theta equal EZ crossed with ER, where ER is this unit vector along OQ. So ER is the unit vector along OQ, and I can probably just write that in here. ER is equal to, I can call it OQ, that vector, divided by its magnitude. Now, once I do that, I actually have an alternate way of being able to describe the position of P relative to O. So to complete this diagram, though, this vector E theta is in the EX-EY plane, and it's orthogonal to ER and to EZ. So if I was to look down on the EZ direction, here's what I would see. So if I look down on the EZ direction, this is the picture that I have. This direction out of the page, start with that. This direction is EZ. So I'm looking down on EZ. And this direction here is EX. This direction is EY. The direction that I drew, that direction ER, is an angle theta from EX. And then E theta completes this right-handed system, and it's this direction right here, which makes the angle from EY to E theta also equal to theta. Now, if you look at the slice through the EZ-ER plane, so this is another picture that will help explain what's going on, is that here's EZ and here's ER. Now, the position of P relative to O, which is that vector right there. So if I think of O as being down here and I think of P as being up there, then this distance, vertical distance, is Z, and this horizontal distance is R. But you can see that R is the component along the ER direction, and Z is the component along the EZ direction. So that implies that the position of P relative to O can be described as RER plus ZEZ. But if I look at this basis, ER E theta EZ, I can see that ER E theta EZ is not fixed. It's not fixed in A. It's not fixed in A. So what I'm going to do is I'm going to define a new frame. I'm going to define that frame as being B. So I'm going to say that ER E theta EZ is fixed in B. So from the information that's given, we can see that B rotates relative to A. B rotates relative to A. And we can see that the amount of the rotation is the angle theta, which means that the rate of the rotation is theta dot, which is the rate of change of theta. So the amount of the rotation is theta. The rate of rotation is theta dot. So the amount of the rotation of frame B relative to frame A is the angle theta. So that implies that the rate of rotation of frame B relative to frame A is theta dot, which is also equal to d theta dt. But it's not enough to just have a rotation rate. We also need an axis of rotation or a direction of rotation, because we need to make this an angular velocity so that we can introduce a rotating frame and we can also introduce its angular velocity. So the axis of rotation or direction of rotation is orthogonal to the plane of the rotation. And the plane of the rotation is the EX-EY plane. So that implies that the axis of rotation of B relative to A is EZ, which finally implies that the angular velocity of B relative to A is equal to theta dot, which is the rotation rate, times the axis of rotation, which is EZ. So we now have two pieces of information. We know that the position of P relative to O can be expressed in the basis ER E theta EZ as RER plus Z EZ. And remember that, as a reminder, ER E theta EZ is fixed in this new frame that I'm calling B. And the angular velocity of B and A is equal to theta dot EZ. So we can now use these two pieces of information to arrive at an expression for the velocity and acceleration of point P as viewed by an observer in frame A using coordinates that are fixed in frame B. And in order to be able to do that, we're going to use the transport theorem. So now let's write this out a little bit more. ER E theta EZ is fixed in B. We want the rate of change of the position of P relative to O as viewed by an observer fixed in A. So that implies that we need to apply the transport theorem. So in this case, the transport theorem will look like this, which is that the velocity of point P in A, which is defined as the rate of change in frame A of the position of P relative to O, is equal to the rate of change of the position of P relative to O in B plus the angular velocity of B in A crossed with the position of P relative to O. Now let's go ahead and compute all these quantities, which is that the rate of change in frame B of the position of P relative to O is equal to R dot ER plus Z dot EZ. Because again, the basis ER, E theta, EZ is fixed in frame B, and therefore the rates of change of the vectors ER, E theta, EZ in frame B are all 0. So the only thing that changes when I'm taking the rate of change of the position of P relative to O in frame B is that the components change with the components change with time, which means that their rates of change are not 0. So the next thing is that the angular velocity of B in A crossed with the position of P relative to O is equal to theta dot EZ crossed with RER plus Z EZ, which is equal to, well, EZ crossed with ER is E theta, and EZ crossed with EZ is 0. So this gives me R theta dot E sub theta. So as a result, I get that the velocity of P in reference frame A is equal to R dot ER plus Z dot EZ plus R theta dot E theta. And if I put all that in the order of the basis, because the basis is ordered to be ER, E theta, EZ, I get that this whole thing is equal to R dot ER plus R theta dot E theta plus Z dot EZ. Now, you can see that that gives us the first derivative, or the velocity of point P as viewed by an observer in frame A, but we want to go one more derivative and get the acceleration of point P as viewed by an observer in A. So then, starting with the velocity of P in A, the acceleration of P as viewed by an observer in reference frame A is given as the acceleration of P in A. Now we're going to take the rate of change of the previous result, which is the rate of change in A of the velocity of P in A. But now this is the part that often gets confusing, because we have to start with where we left off. And where we left off was an expression for the velocity of point P in A expressed in coordinates fixed in frame B. So that means that we have to apply the transport theorem again. So this is d dt in B of the velocity of P in A plus the angular velocity of B in A crossed with the velocity of P in A. And That's just because, just like the position was expressed in the basis ER E theta EZ, so too is the velocity of point P in A. It's expressed in coordinates fixed in frame B. So therefore, in order to get the acceleration of point P as viewed by an observer in reference frame A, we need to apply the transport theorem from reference frame B to reference frame A. So let's take the rate of change in frame B of the velocity of P in A. That's equal to, well, if I use the previous expression, I've got r double dot ER, and then I'm taking the derivative of r theta dot, so I get plus r dot theta dot plus r theta double dot. That's from the product rule for differentiation, plus z double dot EZ. And then the next term is the angular velocity of B in A crossed with the velocity of P in A, and that's equal to theta dot EZ crossed with r dot ER plus r theta dot E theta plus z dot EZ. And if I do the cross products, or the vector products, EZ cross with ER is E theta, EZ cross with E theta is minus ER, and EZ cross with EZ is 0. So I get r dot theta dot E theta minus r theta dot squared ER, and then the last term is 0. So when I add these together, I get that the acceleration of point P as viewed by an observer in A is equal to r double dot. Let's gather up all the terms here. So we have r double dot minus r theta dot squared. Those are all the ER terms. And then the E theta terms, I have an r dot theta dot plus r theta double dot, but I have another r dot theta dot. So that gives me plus 2 r dot theta dot plus r theta double dot E theta. And then the last term stays the same. I get plus z double dot EZ. Now it's important to understand what this means. So when I go back to this expression for the velocity of P in A, where I had r dot ER plus r theta dot E theta plus z dot EZ, this means the following. It means this, that this is the velocity of P as viewed by an observer in reference frame A, expressed in coordinates fixed in reference frame B. That's really important, that this is expressed in coordinates fixed in reference frame B. So even though I'm getting the rate of change as viewed by an observer in reference frame A, it's this key point here. It's expressed in coordinates fixed in reference frame B. So I'm still getting the same rate of change. So this actually, if I put this in parentheses, this is equal to x dot EX plus y dot EY plus z dot EZ. It's just that they're now expressed in two different bases, but it's the exact same vector in both cases. And the same thing applies for the acceleration. So similarly, the acceleration of P in A, which is equal to r double dot minus r theta dot squared ER plus 2r dot theta dot plus r theta double dot E theta plus z double dot EZ is equal to the acceleration, or I should do the exact same thing I did before. It's equivalent to saying it's the acceleration of P as viewed by an observer fixed in reference frame A expressed in coordinates fixed in reference frame B. This is analogous quantity. It's just acceleration now instead of velocity. But again, it's still expressed in coordinates fixed in reference frame B. So that gives us all the information for cylindrical coordinates. So the last thing that we're going to do is we're going to define what are called spherical coordinates. Now, this is a little bit more complicated than what we had done previously. So I'm gonna first describe things with the angles, and then I'll get into the diagram afterwards, which is that we're going to define new variables again. So we're going to introduce new variables. And I'm going to call these variables rho and phi. And it's going to be, these new variables are going to be introduced as follows, which is that first what I'm going to do is I'm going to define x, y, and z. Now you notice that previously I did it with just x and y because with cylindrical coordinates there was no change in z. But now I'm going to be doing it with changes in x, y, and z. So the first thing is that I'm going to define is as follows. So x is going to equal rho times the sine of phi times the cosine of theta. Y is going to equal rho times the sine of phi times the sine of theta. And then z is going to equal rho times the cosine of phi. Now, in order to be able to see what this looks like, let's put it on the diagram. I'm going to add to the diagram from what I had before. So here's what the diagram looks like now, which is previously I had two bases on this diagram. The bases were EX, EY, EZ. And then I had another basis which I had introduced, which was ER and then E theta and again EZ. I had this angle theta. That angle stays there, by the way. I still had these components which were X, Y, and Z. So I had X, I had Y, and then there was this position of this point which was up here. Point P was up here, O was down here. This is the same diagram I had before. It's just that I'm adding, again, more information to the diagram, which is now I'm going to introduce this angle phi, and I'm going to introduce this distance rho. Rho is the distance from O to P, and phi is the angle between EZ and the position of P relative to O. So now what I'm going to do is I'm going to define two new vectors. I'm going to define the following. I'm going to say let UR equal the position of P relative to O divided by its magnitude. which is just the position of P relative to O divided by rho, the way I had it. And the vector u theta is going to equal e theta. So I'm just going to set that equal to e sub theta. So they're the same. And then what I'm going to do is I'm going to take the vector u theta crossed ur to give me u phi. So u theta cross ur is going to equal u sub phi. Now that's going to create a new basis. So there's a direction down here which I have to draw this way. This direction is u sub phi. So the new basis is ur u phi u theta. It's in that order. Now in order to be able to see what this looks like, it's again useful to be able to draw this in a projection. So let's look at this in the EZ-ER plane. It's a lot easier to see it in that plane than it is to see it in this three-dimensional diagram. So if I look at this plane, which is this EZ-ER plane, this direction is UR, and this angle is phi. Well, because this has to be a right-handed orthonormal basis, this direction is u sub phi. It's the same direction I had in the previous diagram, except for now I've got it in 2 dimensions. It's a lot easier to be able to see what's going on. And this angle is also phi. Now, the direction into the page, so draw it with an X, that direction is u sub theta, which also happens to be e sub theta. They're the same. So again, the ordering of the basis is UR, U phi, U theta, which implies that UR crossed with U phi is equal to U theta. First cross with the second is equal to the third. Now, what we can see from this basis is that if you look back at the way I defined UR, we have that the position of P relative to O is equal to rho times UR. But notice that UR U phi U theta is not fixed in frame A, and it's not fixed in frame B. So this basis is now going to be fixed in a new frame. And we're going to call that frame reference frame C. So given that this is fixed in this basis, UR U phi U theta is fixed in reference frame C, in order to be able to obtain the position and velocity, the velocity and acceleration is viewed by an observer in reference frame A, because this basis is fixed in reference frame C, we need to apply the transport theorem. From C to A. So in order to be able to get this transport correct, we need the angular velocity of reference frame C in reference frame A. So we have to somehow figure out how to get that angular velocity. Well, there are a couple things that we already have. So it's really important to notice that we already have the angular velocity of B and A. That's theta dot times EZ, and that hasn't changed. So that part is okay. We have omega BA. Now we need omega CB. And if you look at this diagram here, you'll actually see that omega CB, which is how reference frame C rotates relative to reference frame B, is equal to phi dot times u theta. So now we can use these two pieces of information together to be able to figure out the angular velocity of reference frame C as viewed by an observer in reference frame A. So then, from earlier, we have that the angular velocity of B in A is equal to theta dot times EZ. And we now have that the angular velocity of C in B is equal to phi dot times u sub theta. But this is now not expressed in terms of one right-handed orthonormal basis. And why is that the case? That's because of the diagram. Let's draw the diagram again. We see here that here's ER, and then here's EZ, and here's UR, and here's U phi. So EZ is not one of the vectors in this basis UR, U theta, U phi. So as a result, or UR, U phi, U theta. So as a result, what we have to do is we have to express EZ in terms of this basis UR, U phi, U theta. So if we look at the diagram, we see that EZ is equal to cosine of phi times UR minus the sine of phi times U phi. And it's minus because if I extend this vector, this is in the opposite direction, this is minus U sub phi. And so it's cosine of phi times UR times minus sine of phi times U phi, which then gives that the angular velocity of B in A is equal to theta dot times cosine of phi UR minus the sine of phi times U phi, which then implies that the angular velocity of C in A, which is equal to the angular velocity of B in A plus the angular velocity of C in B, is going to equal the sum of these two expressions, which is theta dot cosine of phi UR minus the sine of phi U phi, and then I have plus phi dot times U sub theta, which gives that the angular velocity of C in A is equal to, well, let's write this out. So the ordering of the basis is UR, U phi, U theta. So it's theta dot cosine of phi UR minus theta dot times the sine of phi U phi plus phi dot times U sub theta. So that's the angular velocity of reference frame C as viewed by an observer in reference frame A. So then, rewriting from the last page, omega CA, we have omega CA is equal to theta dot cosine of phi UR minus theta dot sine of phi U phi plus phi dot U theta. So now we have everything we need to be able to apply the transport theorem from reference frame C to reference frame A. So we can recall that the position of P relative to O is equal to rho times UR, which means that the velocity of P in reference frame A, which is equal to the rate of change in reference frame A of the position of P relative to O, is equal to the rate of change in reference frame C of the position of P relative to O plus omega CA crossed with the position of P relative to O. So now let's take these piece by piece. First, the rate of change in reference frame C of the position of P relative to O is equal to rho dot times UR. Because again, the basis UR, U phi, U theta is fixed in reference frame C, so those basis vectors aren't changing in reference frame C. The next quantity is omega CA crossed with the position of P relative to O. Well, that's equal to theta dot cosine of phi UR minus theta dot times the sine of phi U phi plus phi dot U theta crossed with rho UR. Now let's do out this cross product, which is UR crossed with UR is 0. Now the ordering of the basis is UR, U phi, U theta. So U phi is the second vector and U theta is the third vector. So the third crossed with the first is the second, and the second crossed with the first is minus the third. So I've got rho theta dot times the sine of phi, and then U phi crossed with UR gives me minus U theta, so that cancels out the negative sign. And then U theta crossed with UR is U phi, so I get plus rho phi dot U phi, which then implies that the velocity of point P in reference frame A is equal to rho dot UR plus rho theta dot sine of phi U theta plus rho phi dot U phi, which we can now reorder this again the same way we did before. So we then have the velocity of P in A is equal to rho dot UR plus rho phi dot U phi plus rho theta dot sine of phi times U sub theta. So now we can take the rate of change again to get the acceleration of point P in reference frame A. So then the acceleration of P as viewed by an observer in reference frame A is given as the acceleration of P in A is equal to d dt in A of the velocity of P in A, which is equal to d dt in C of the velocity of P in A plus omega CA crossed with the velocity of P in A. Now we need to do the same operations on the velocity as we did on the position, which is that we have that d dt in C of the velocity of P in A is equal to, well, let's do this first. So again, UR, U phi, U theta, they're fixed in reference frame C. So the only thing that changes are the components. So this gives me rho double dot UR plus rho dot phi dot plus rho phi double dot times U phi. And then this last term is a little bit long, so I'm going to put it on the next line, which is plus, I get rho dot times theta dot sine of phi, and then I get plus rho times theta double dot sine of phi plus theta dot phi dot cosine of phi, that whole thing is multiplied by u sub theta. I just use the product rule for differentiation. So first I have to take rho dot times the quantity theta dot sine phi, and then I have to take rho times the rate of change of theta dot sine phi, which is theta double dot sine phi, plus theta dot phi dot cosine phi. Now, the next thing that I need to do is I need to compute the angular velocity of C in A crossed with the velocity of P in A. Well, first I need to go back and I need to get that angular velocity, and then I need to insert that expression here. So we have theta dot cosine phi UR minus theta dot sine of phi U phi plus phi dot U sub theta, and that's crossed with rho dot UR plus rho phi dot U sub phi plus rho theta dot sine of phi times U sub theta. So this expression is rather long. So what we're going to do is we're going to first transcribe it to the next page so that we can clearly see what's going on, and then we'll do the full calculation after that, and then we'll add it in to the other part of this, and we add the two things together. So we have d dt in C of the velocity of P in A is equal to rho double dot UR plus rho dot phi dot plus rho phi double dot times U phi plus rho dot theta dot sine of phi plus rho theta double dot sine of phi plus rho theta dot phi dot cosine of phi, the whole thing times U sub theta. So that's that part. And then we're going to rewrite omega CA crossed with the velocity of P in A, and that's equal to theta dot cosine of phi UR minus theta dot sine of phi U phi plus phi dot times U theta crossed with rho dot UR plus rho phi dot U phi plus rho theta dot sine of phi U sub theta. So this last result is equal to UR crossed with UR is 0, UR crossed with U phi is U theta. So we get plus rho theta dot phi dot cosine of phi times U theta, and then UR crossed with U theta is minus U phi, so you get minus rho theta dot squared cosine of phi sine of phi times U phi, and then U phi crossed with UR is 2 crossed with 1, which gives plus rho dot theta dot times the sine of phi times U theta, and then U phi crossed with U phi is 0, and U phi crossed with U theta is UR, which gives minus rho theta dot squared sine squared phi times U R, and then we have U theta crossed with UR, which is again 3 crossed with 1, which gives plus rho dot phi dot times U phi, and then I've got minus rho phi dot squared times u r. So now we can combine all of the like terms to get the following result, which is that the acceleration of point P in reference frame A is equal to, so let's first gather up all the UR terms. We have rho double dot, and then we have minus rho theta dot squared sine squared phi, and then minus rho phi dot squared. Now we can do the u phi terms. We have rho dot phi dot plus rho phi double dot in the first part, and in the second part we have minus rho theta dot squared cosine phi sine phi, and we have another rho dot phi dot. So we have 2 rho dot phi dot plus rho phi double dot, and then we have minus rho theta dot squared cosine of phi times the sine of phi times u phi. And then the last term is the u theta term. So if we look at the u theta term, we have a rho dot theta dot sine phi. So if we look down in the second part, we also see we have a rho dot theta dot sine phi. So there's 2 rho dot theta dot times the sine of phi. The next term is rho theta double dot sine phi. There's no other term like that in the other expression. So we have plus rho theta double dot times the sine of phi. And then we have a rho theta dot phi dot cosine phi. And then you see we have another rho theta dot phi dot cosine phi. So that gives 2 rho theta dot phi dot times the cosine of phi. And that's times u sub theta. So there's the expression for the acceleration of point P as viewed by an observer in reference frame A. And again, this time it's expressed in coordinates fixed in reference frame C. So now let's move on to a discussion of the key results. That were studied. The first is the concept of a rotating reference frame. So now, whenever we had a frame B that rotated relative to a frame A, then we needed to compute the angular velocity. So if B rotates relative to A, then it was necessary to determine the angular velocity of frame B as viewed by an observer in frame A. Even more so if the problem contains multiple rotations, and you say that is more than 2 reference frames, then it was necessary, or it is necessary, to add angular velocities. And of course, that looked like the angular velocity addition rule, which was something like omega CA is equal to omega BA plus omega CB. And in all these cases, the key idea is when there's a rotating frame, we need to apply the transport theorem. And the transport theorem is always applied from the last frame back to the first frame. So it's between the final frame and the initial, which is called base reference frame. And that is also known as the target reference frame. So that takes us to the end of this particular lecture. So now let's summarize what was studied in this lecture. First, we provided definitions of position, velocity, and acceleration of a point. Second, we developed the position, velocity, and acceleration in terms of commonly used coordinate systems. And in particular, we studied parameterizations of position in Cartesian coordinates, cylindrical coordinates, and spherical coordinates. And finally, we provided a brief discussion of the key concepts studied. And the results developed in this lecture will be the basis for future work where we solve problems in kinematics and then we use kinematics together with kinetics in formulating differential equations that describe the motion of mechanical systems. But for now, that'll be the end of this particular lecture. We'll stop here and then we'll pick it up next lecture.